Yeah.
Okay.
If I keep my upbeat attitude, it'll like push me through and keep me excited, and like I'll remember things. Here you go.
Maybe I do it.
Maybe.
Get those bootstraps.
Might as well give it a try. Thanks, Philip.
The first question says, what's the average value of y equals x squared from 0 to 2? So we gotta first look at like, what does that even mean? So you could, for example, a way to like brute force an average value. I'm sorry, that's 2 of it. That's 2. Well, yeah, you could go, well, I mean, let's see what happened. What would happen if you did this? You said, well, I mean, I don't know. 0 gets you 0, so 0 is a y value. 1 gets you 1, so 1's a y value. And 2 gets you 4, so 4 is a y value. If you add those up and divide by the number of values, you get 5/3. Now, is that the average value of the function? No, you would hopefully, if someone tried to make that claim, it could be 5/3. As far as is that a general method that'll give you the average value, you might go, well, no, because you kind of neglected an infinite number of points, right? There's an infinite number of points along there. So the question is, if you could somehow tally up an infinite number of y values and then divide by the number of y values, then that would give you the average value. So the actual answer would be, it's a geometrical answer. So you'd say, well, what if, suppose we looked at this area and made the argument that the average value would be the value that if this were a rectangle would have the same area. How do you guys feel about that argument? So I'll give you maybe a more physical example would be, suppose this was a velocity versus time graph, right? How would you find the average velocity? Well, the average velocity would be the overall displacement divided by time, right? Well, how do you get the overall displacement from a velocity time graph? You find the area. So what you'd say is like, you basically say, well, I'm going to take the integral of the velocity function to find this area, and then divide it by the span, the horizontal span of the region. Does that make sense? Which is the same idea you have here. That's how you'd find what's a single y value that would have the same effect area-wise as this curve. So, all right. Anyway, let's get to the answer. So it would be the average value of the function would be the integral of the function from 0 to 2. And what am I going to, once I have that area, what would I do with it? What would I divide it by? 2. Divide it by 2. Like that. So, let's see what we get.
Wait, why do you divide it by 2?
For the same reason that, so back to this example, suppose this was 3 hours. And suppose that we calculated that you drove, say this is you driving your car, this is your velocity function. Say you traveled 120 miles was your total displacement. And we knew that took 3 hours overall, you would divide by 3 to get your average thing.
So we put the 2 there or we divide by 2 because it was traffic 2.
Yeah, so we're dividing by 2 because that's the horizontal, the width of the interval. So, and again, it's back to this too. It's like if I took the area and divided it by 2, it would tell me how big that height is. So, anyway, so the integral is 1/3 x cubed evaluated from 0 to 2. So carefully plug in the 2, get 8/3. And you plug in the 0, get 0. And so what's our answer? 4/3. So a third of the way, a third of the height, basically. So it turns out,
Could you explain your rectangle? I don't understand what you're getting at.
yeah, okay, so let's use the same numbers and just talk about velocity time, and then it'll connect to the rectangle. So like, suppose this is your velocity time graph, right? And let's suppose that your velocity time graph is parabolic. And suppose that this is a 2-second interval, right? And so this area here represents the displacement. So the integral that we took is 8/3, right? Does that make sense? Still with me? Okay, so now what we're saying is there a velocity that we could have just traveled at the entire time and gotten that same displacement without ever changing speed? So what we're looking at is, well, we're looking for this special value called the average. Yes, Jesse's favorite. So what we're saying is, suppose there was an average velocity. Could we have picked in advance some velocity to just travel at constant velocity in a way so that the displacement was the same? Does that make sense? So in this case, it's okay, with this weird quadratic velocity function, we ended up traveling 8/3 of a meter. What's the average velocity? So the way you calculate that is you go, well, okay, this was 2 seconds, right? So I'd say V average times 2 has to equal 8/3. And there's our answer. 4/3. So does the rectangle thing make sense? So we're basically, we're trying to answer this question of, is it possible to take this, and there's some context where it makes no sense to look at the average value. But if you're looking at, like, say, long-term behavior, so displacement's a good example. Oh, my object followed this strange velocity function. What was the average speed that entire time? What was the average velocity? It's helpful for that. So let's do a couple more examples. Hopefully it'll make sense for you. Look at the next one. So number 2. Why don't you try 2 yourself? That one's a pretty easy integral. The calculations are fairly straightforward. And we'll compare answers. So we're getting close. Almost done. Who's got an answer they're confident with? Do I have the final one yet? Let's give everyone a chance to, I think some people are just barely finishing up here, so. By the way, keep in mind, there's a really easy way to check if your answer makes sense. Doesn't guarantee you're correct, but if you get an answer, if you get a number bigger than 3, then obviously you made a mistake, right? So again, it's like, oh, I've got this infinite collection of y values. What's the average of all those numbers? By the way, just looking visually, do you think the number is bigger than 1.5 or smaller than 1.5? Bigger. Why?
More of the time is over long enough.
That's a big.
Yeah. It spends more time closer to 3, right? If this were a velocity graph, you'd say, well, he kind of gets up to a pretty good speed pretty quickly. He spends most of his time close to 3. So we should expect, so what's your answer, Caleb? What'd you get?
I got 2.
He's got 2 exactly?
I
Okay,
got 2.
sweet.
I got
So that's pretty interesting. So you get integral from 0 to 9 of the square root function. And then you're gonna just take that answer and divide it by 9. And so, yeah, you get x to the 2/3 of x to the 3/2. Signs all messed up, right? So you get, plug in 9, a little bit of arithmetic here. What's 9 to the 3/2? 27. And 2/3 of 27 is 18. Plugging in zeros is a little bit easier. And so, yeah, pretty kind of remarkable. You just get an integer. So it turns out your average value, excuse me, is right there. Okay. I try to give you a couple extra, some word problems that just give you some context in which you might want to find the average value. Temperature is a good one. That's one that gets applied in real life pretty frequently. So say you had some system. So say this is the temperature of the system versus time. You might be interested in what was the average temperature. Say the temperature is fluctuating with like, I don't know, max of 100 and a min of 75, and just kind of like, well, what the computer would do. So say you take this data with an instrument. The computer is going to integrate this using a Riemann sum, which I'll show you about later. Basically, if you're wondering, what it would do is it would break this into a whole bunch of tiny rectangles. And since it's a computer, it can do that really fast. It would break this into like 1,000 rectangles. And it would find the area. And then it would take that area and divide it by however wide this interval was. And tell you what the architecture is.
So is there a certain number that becomes acceptably close to the average? Because we talked about you can't just break it into like 2 because that's not close enough.
Yeah, well, don't even think about average. How about just the integral? So say I have some function, right? And I want to know what's the, let's say between 2 and 7, how much area does this curve have between 2 and 7? That's a question you might ask. And yeah, you would say, well, how precise do I want to be? Because a lot of functions out there, you can't integrate them by hand. They don't really have a nice antiderivative. So what you have to do is take the computer and say, well, computer, break this into 1,000,000 rectangles. And 1,000,000 is going to be pretty dang good, barring, I mean, if the function has some crazy spikes in it, for example, you can make a function that has like insanely like sharp spikes that makes it hard for a computer to analyze it. But if it was nice and smooth like this, even 100 rectangles from 2 to 7 would get you like within, I'm sure, like within a tiny little margin of true answers. So it just depends on how accurate you want to be. There's some interesting stat where you can say like, because people memorize pi to like 1,000 digits. Well, I want to say if you know it to like 50 digits, then that's sufficient to estimating the circumference of the observable universe to within the size of like one hydrogen atom. If you think about, because 50 decimal places gets you that degree of accuracy. So it might not be, maybe it's 100. You have to look that up, but it's kind of interesting. It's kind of like, oh yeah, it's a surprisingly small number for getting within one hydrogen atom of universe circumference. Okay, so that's kind of all I need to cover about average value. Bear in mind, the last thing is, where did this 9 come from? This 1, 9. It's not just that 9. It's really the width of the interval. So like on this one, if you wanted the average value between 2 and 7, what would you be dividing by? Be dividing by 5. Is everyone okay with that?
Yeah.
I'm going to move on and cover one extra thing, just kind of front load this so you'll have everything you need to know. This is going to be a short problem set. There's not a ton of info here. The next thing we're going to cover, I used to lump this in with the next unit, but then I realized it was kind of too much information. But looking forward, we're going to start taking this and revolving it around the x-axis and calculating like volumes and stuff, which I think is pretty interesting. Okay, this next part's super easy. Area between curves. What? What's wrong?
Have you guys done these all already? Were you, so, I'm just so scared.
Okay. So we got average value. You just integrate, divide by the width of the interval. Pretty straightforward. How about area between curves? If you're wondering, how do these really connect conceptually? Not really. I mean, a little bit, but technique-wise, they're almost identical. So that's why I put it together. So this first question, 11, just says, well, if you'll allow me here, just quick general idea. Suppose you got a function, here's f, then you got a different function, here's g. You got f and g. And suppose you wanted to know how much area is there trapped between these curves, say between 3 and 8. Whatever, made up those numbers. If you wanted to know this area here, who's got like a conjecture on how you do that? Yes, sir.
You find them both and subtract the smaller one from it.
Very good. So all you would do, because think about, if I looked at the integral of f between 3 and 8, well, that would be the area from this curve down to the x-axis. And if I subtracted the integral from 3 to 8, of g would be this area down here, right? And so if I subtracted them, I'd be left with the leftover. Does that concept make sense to everyone?
Yep.
And then one other thing is, well, we know about integral properties. Do you think which is easier, to do 2 separate integrals and then subtract the numbers? That may be the case, but most of the time it's going to be easier just to combine them into a single integral like that. Does that make sense? So in practice, what do you do? 11 says you've got, what's the area trapped between a y equals x squared parabola and the line x plus 2? So why do you think I put little dots on those intersections?
Your interval.
That's going to be telling us where our interval is. Most of the time, solving like when do they cross is actually usually pretty easy. Because you can imagine, like, you know, if they crossed at points like 1 plus root 7 over 2, like some sort of irrational number, that would make the integral very cumbersome. So typically in like textbooks and exams and stuff, they tend to intersect at like integer points. So with that in the back of your mind, little guess and check tells you what x value do these cross at over here. 4.
2, 4, and -1.
Oh, x value.
Oh, x.
And so as far as showing your work goes, just show this is what I'm solving to find the intersections. So to find the Okay. I'm solving this, which has 2 is a solution. What else? -1. If you draw the picture, it gives you a pretty good hint if you draw it semi-carefully. So from -1 to 2. Everyone's okay with that? And then we're going to shade in the bounded region. Okay. Kind of a weird shape, right? Flat part and a curved part. And then here's sort of the beauty of calculus is watch how easy it is to find this area. You might, in a lot of areas are very complicated to find, but in this case, because of what we know about integrals, we can just go, the area is the integral from -1 to 2. And then who's on top?
No, two. Oh.
Yeah.
The x plus 2 is above.
I thought he meant on the top of it.
So that, how do I feel about that? This is sort of my f minus g right here. Okay. And the calculation is, on some of these, we're going to start more like when we get to the volume stuff, we're going to start maybe just say set up the integral because that's the interesting part. The calculation at a certain point, once you've mastered these calculation techniques, it gets a little boring. But anyway, my integral would be, what's the integral of x? 1/2 x squared. Integral of 2 2x minus 1/3 x cubed. This one's certainly not, it's not that easy because you gotta plug in 6 things or do 6 plugins, which is never trivial. Okay. So let's plug in the 2. By the way, I've been looking at your quizzes and they're pretty good for the most part, but there weren't that many arithmetic mistakes, but there were more than I kind of thought there'd be. So just be careful on this part. I don't know if it was because of rushing or what, but anyway. Plug in 2, so you get 4 halved is 2.
Yes, it was rushing into things.
This step here might help out. One extra step. So plug in 2 gets you 2. Plug in 2 here gets you 4. And lastly, plug in 2 here gets you what? Minus 8/3. Okay. Now let's plug in the -1. It's me 1/2. How about there? -2. And then be careful. Minus 1/3 of -1 would really be plus 1/3. That feel okay for everyone? Okay. And so I might show one intermediate step here, which is to go, well, I've got 6 minus 8/3. How many thirds is a 6? It's 18/3. So 18/3 minus 8/3 is 10/3. And then over here, ooh, this one's kind of ugly, isn't it? I've got a 1/2 plus 1/3 is 5/6 minus 2, which is 12/6. So what do I have there? -7/6. Make sense? 26 plus 7/6 would be,
Is it minus 7?
well, it's plus, right? Because we're going minus a negative. Is that right? Did I have that right?
Yeah.
So 27/6, and those are both divisible by 3, so yeah, sorry, I kind of ran out of room here, painted myself into the corner. And I'm realizing now there probably was a more clever way to do that because you had -8/3 minus 1/3, which makes -3. So you can go 6 minus 3 is 3, 3 plus 2 is 5, 5 minus 1/2 is 4.5. So oopsies, that works too.
Oh,
Yeah.
where did the half x squared, that's the interval, right?
This one?
Yeah.
That's just the antiderivative of x. So it's just
Oh,
x to the 1
okay.
power. So we're just raising that up to the 2 and then dividing by 2.
Oh, yeah, this is, we don't have to do the interval on this.
Oh yeah, we're not dividing.
I messed that up.
We're not. Yeah, that's so that's the thing you got to keep straight is on average value. You're going to be dividing your integral by the horizontal width, but on these you're not going to be dividing by, say for example 3. You're not going to divide by 3. Okay. And you guys all are familiar with how to. So if you're say doing this outside of class or you need to check your answer, the computer can check that for you. Desmos, for example. You just type that in. Okay, let's do one more. Last one. Then I'll shut up. So look at 12. What might catch your attention about 12? What makes 12 maybe a little bit different than the last one?
3.
3? What do you mean?
Oh, I know. Well, yeah.
There's just 2 functions.
There's 2 separate areas.
Yeah.
Yeah. Exactly. So on the left side of the picture, so if we're calling those F and G, then there's a region where F is above G and there's a region where G is above F. So what that means is we got to kind of calculate them separately. Because if you don't, then what's going to happen is in your integral, it's going to treat some of that area as negative and some as positive. It's going to throw off your answer. Does that make sense? I'll elaborate on that more specifically in a second. But so anyway, where do these guys cross?
And 1, 0.
1 and 0. And then of course the horizontal piece just tells you where to stop basically. So you got this area. My drawing is not super good, but everyone understands why you can see where they cross at 1. So, when does square root of x equal x? Well, when x is 0 and 1. So here's 0, here's 1. Does that make sense? So, and then, are there any questions on why? If I go, say I look at this line and I say, oh, the line's on top. So I go x minus root x. Well, here, x minus root x is a positive value, but over here, x minus root x is negative. So that area would all turn negative. So I can't do that. What I got to do is go, it's going to be a little bit of a doozy here. It's the integral from 0 to 1. So from 0 to 1, the root x is on top. And x is on bottom. So we're totally fine on how that's going to produce a positive number. Okay. And then the integral from 1 to 4 of x minus root x. There's nothing super tricky happening here. Like if I had these swapped, it would just produce the opposite answer. Does that make sense? Once we get the number out, discuss that for another couple of seconds. But. Okay, integration time. Let's see, x to the 1/2 becomes x to the 3/2 times 2/3. Right. And then this x becomes 1/2 x squared. 1 from 0 to 1. Plus this guy. Luckily, I don't have to do, there's not much thinking left. I already did the antiderivative, so this was just going to be the opposite of that. So Still feel okay? No questions? Okay. This one's actually pretty easy, right? Plugging in 1, so plugging in 1 gets you 2/3 minus 1/2. And then plugging in the 0 just gets you 0, right? So that's the first one. By the way, what kind of number is that? It's positive. What does this number represent?
The first little section.
That little area right there. And then this guy over here, it's a good way to just, as you're doing any math thing, as you're moving, check, what am I doing, right? What does this number mean? Okay, over here, let's plug in the 4. 4 squared halved is 8. Plug in the 4 here. What's 4 to the 3/2 power? 16.
Oh,
Well, sorry, it's gonna be 16 after you multiply by 2, but 4 to the 3/2 is 8, right? You square root it, then you cube it. Square root it turns it into 2, cube it turns into 8. 8 times 2/3 is 16/3. And then don't forget to plug in the 1, common mistake. Plugging in 1 gets me 1/2 minus 2/3. How do we feel about that? Sorry. Okay, so let's do a little bit of arithmetic here. 2/3 minus 1/2. 1/6. 1/6. So we've got a 6. And then here, let's see, we've got, this would be negative 1/6, but we're subtracting it. This is a plus, so we have minus negative 1/6. So that's really adding another 1/6 on, right? And then we've got plus, 24/3 minus 16/3 is 8/3. Do I still have you guys make sense?
Yep.
Okay, so I have, that's 1/3 plus 8/3. That's pretty neato. I wanted to show you something. Last thing. Mr. Desmos. Here's some food for thought. So we can figure this out. This will be pretty impressive, but could you have done this in a single integral? Not by hand. Say you have a computer handy. I'm going to show you on the computer in a second, but does anyone have an idea of how would you lump this into a single integral that just does it all at once?
Absolutely.
Okay, so what would be the whole integral? What would you do?
Oh, it'd be like integral from 0 to 4. 0 to 4 of the absolute value of, I don't think it matters which one you put in first.
Perfect. Yep. Exactly. Yes. So let's ask Desmos. Let's ask Desmos if our work was correct. So think about that. Why does that make sense? So I go to Desmos. What's nice about Desmos is you can graph that you started with, just to make sure you're visualizing everything correctly. Great. And then go, okay, what's the integral of?
How do you put the integral in?
I typed in INT. 0 to 4, and it's x minus square root of x dx. Oh, what did I forget?
Absolute value.
So there you go. There's your problem if you don't have your. So what that's doing is, who got treated as negative? That guy, the left guy, or the right guy? If I go x minus root x, left guy would get treated like negative number. So I got to go absolute value bars. And there you go. Desmos confirm. The answer is 3. So all that's doing is We're going to get into the details of this later, but in a sense, an integral is chopping this up into an infinite amount of little slivers. And if you put an absolute value bar down, then it's going to treat each sliver as positive. Whereas if you don't have the absolute value bars, it doesn't do that. So, all right. I hope you found that somewhat interesting.